Don't forget to say what.
No, you do plus and minus.
Where did you start action? So A is going to be it's just going to be whatever it is that's on, right? And B that's opposite. So we'll start with B. Triangle. And then it would go to A. So whichever direction it is. Or I would put it down over that way. So it's written out. That's good. So there's two ways you can do it.
Well, I mean, like straight down, straight down, positive even straight down.
Going in negative, positive Y, and positive X.
Be going
Or is that negative X because
Yeah.
Isn't it -4 on the z, so wouldn't a be down?
Yes. You waited that long to tell me that?
Oh,
Jeez, you guys, come on. Don't ever do that again.
It was -2, 3, -4.
Is that one wrong too?
Your B was correct.
Yeah, your B was correct.
I'm not going to do them again. How about, is there another question or two that you want me to talk about by request?
What's the unit basis form of number 6?
Talked
The
about
unit
that
basis
Friday.
Okay.
Remember what that was? 2 ways to write. Yeah, 2 ways to write a vector. Yeah. Number 8. So what is A plus B? So A plus B is. Okay, so then here's something that the TA picked up when I was grading. You have to be really careful and precise about when something is a vector versus when something is a scalar, like the magnitude of a vector. So you would don't ever write A plus B and then write a number. Why? Because what is A plus B? That's a vector. So you're gonna, when you write A plus B equals something, you're gonna write a vector either in component form or standard basis form. So I'll go ahead and write it in component form. So A plus B in component form is 1, 0, and -2. Okay. What's the and then what's the magnitude of A plus B? Because A and B are the vectors from 0, 0, 0 to these, then these are the vectors A and B. So the vector A is -2, 3, -4. And the vector B is, and this is only why, because to find A, we put its tail at the origin. Therefore, these points are also the components of the vectors. 3, -3, 2. So now do you see why A plus B is C is -2? You got it now? All right, so what's the magnitude of A plus B? Square root of 5, okay? So how about this? So here's, to get the magnitude, it's going to be the sum of the squares, just like in 2 dimensions. How do you like what I wrote? Is it good? What I wrote is okay? No. It's not okay. This is what a lot of you guys are doing. There's a difference between a value, a scalar, and a vector. You can't set a vector equal to a scalar. You see? And so you have to be careful but you have to communicate precisely. This is a vector. Don't set it equal to its magnitude. A vector and its magnitude are not equal things. A vector has direction also, right? So what did I mean to write? Take this out of here. Start something new. What did I mean to write? The magnitude. And so sometimes they use double bars, sometimes they use singles bars. It means the same thing. The magnitude, either single bars or double bars. The magnitude of A plus B is the square root of the sum of the squares, is the square root of 5. Okay, be careful, all right? If you're writing a magnitude or a scalar, don't say it's equal to something that's a vector, like this. Do you guys see the difference? Okay, so what was, all right, so if a plus b is what? 1, 0, negative 2, we want to draw its tail at 0, 5, 0. So 0, 5, 0 is at 5 on the y-axis. Okay, and then now from there, we're going to draw the vector 1, 0, negative 2. What do these numbers mean? 1, 0, and what does the 1 mean? A change of 1 in the x direction from tail to tip. And what does the 0 mean? No change in y from tail to tip. And negative 2 means a change of negative 2 in z from tail to tip. So we're going to go to get the, if we're going to put the tail there, its tip is going to be 1 in the x direction, 0 in the y, and then down 2. So then it would look like this. And that's A plus B. So this is coming out 1 unit at you, 2 units down below, and then neither left nor right, starting from 0, 5, 0. Does it make sense? Number 8, does it make sense? Okay, one more request. Yep, he was first.
Number 9.
Yeah?
Just more like the determining just visually.
Okay.
Direction.
Sure. Okay, so we got A and B. So where does A go? I obviously butchered this. Negative 2, 3, negative 4. Something down like this. Is that like A? Okay. Negative 2, positive 3, and down 4. Maybe. Okay, yeah, that's pretty good. All right, and then B. 3, negative 3, 2. So we know that A minus B is going to be, it's the difference between these two, right? It's the difference between these two. So it's going to be a vector that when you put them tail to tail like that, well, so the question is, which way is the point? So if it's A minus B, so there's a couple of ways to think about this. So A minus B is going to be what? How much greater A is than B? How much greater A is than B? And so you could think of this as like final. When you do a subtraction, you're doing like final minus initial, right? So then which way would that point? If this is final minus initial, then the final point or the tip would be at A. And then the initial or the tail would be at B. So it'd be this way. So that's one way to think about it. And then you can just, then you can see, so if this is A minus B, then now make this triangle into a sum problem to check. So what addition problem would it be? Would it be B plus A minus B equals A, or A plus A minus B equals B? Yeah, so our first would go here, and then we go tip to tail, and then we go here. So B, according to my picture, this would be true. And then we can check the math, right? So according to my picture, this is what's true. Head out B, then start here and head to here, and that's the same as summation, same as A. Now, mathematically, is that correct? B minus B goes away, left with A equals A. Questions on subtraction? But yeah, so this vector A minus B, it's like, how much is A different than B? How much is A different than B? Like, what's the difference between the two? Well, there's this much difference. of A from B, right? There's this much difference of A from B. Or final minus initial, right? Final value A minus initial value B gives you that much difference starting at B, ending at A. Okay, so hopefully we're starting to get more comfortable in R3. So we want to do lots of exercises so we're getting more comfortable in points and vectors in R3. All right, let's go on. So we go on. You can put those sheets aside. So point C is x1, y1, z1. And point D is x2, y2, z2. Then what's vector CD? Write out what vector CD. So point C is x1, y1, z1, and point D is x2, y2, z2. Question? Yeah. K. Yes. Okay. So everything we've done so far, although I haven't explicitly talked in R3, it just is the natural kind of thing in R3. So yes, for unit basis form. So we'll do that in a second. But yes, it'd be I, J, and K. Let me draw those. So I is still for the x coordinate. So what's the vector I in R3? What's the vector I in R3? 1, 0, 0. What's the vector J? 0, 1, 0. And so then in the Z direction, K is 0, 0, 1. Vector. Then every single vector in R3 can be written as a linear combination of those three, right? With scalar multiplication and addition, you can create any vector out of I, J, and K. Right? By adding the right number of i's together, and the right number of j's together, and the right number of k's together, you can reproduce any vector. So that's called the unit basis form. Okay, so what is the vector CD? Yep. The first component is going to be x2 minus x1, right? It's the change. The change in x from C to D will be the x component. Y component? Easy now, right? And then Z2 minus Z1. Okay, what's the magnitude of CD, right? So what's the magnitude of CD? So we're going to start a new statement, right? Because now we're going to write a scalar, not a vector. We're going to write a number. So this is a new statement now. And we're at the magnitude of CD. And so it's like a kind of a three-dimensional Pythagorean theorem. Three-dimensional, like it's like the diagonal of a box. The diagonal of a box. You can show that if you the Pythagorean theorem on one side, that gives you the diagonal of one side. Combine that with a third dimension, and you get the diagonal of the box. And so then it would be sum of the squareds, square root, just like the Pythagorean theorem, but now with three coordinates. This is a three-dimensional version of the Pythagorean theorem, which you could prove in 2 steps, right? Make a box. Make a box. Get the diagonal of one side of the box. Combine it with the third dimension. That makes another right triangle. Get the diagonal of the actual box. That's length. So not only is that the magnitude of the vector CD, but then, so what is that in space then? That value then of the points C and D, what is that? So if that's the magnitude of vector CD, then what is that relative to the points C and D? The distance between them, right? So if it's the magnitude of that vector, then it's the distance from C to D. So then this is also, it's the magnitude of a three-dimensional vector. It's also the distance between the points at the end of the vector. Because that's how we represent magnitude when we draw a vector. It's the length of the vector. So then this becomes our distance formula as well. Distance from C to D. Does that make sense? You see how it's both, right? If you're talking about a vector, it's the magnitude of the vector. If you're focused on the 2 points, it's the distance between the 2 points. Same value. Questions about that? Okay, well, that being said, if I have some point, say ABC, that's a fixed point. Fixed point ABC. Call it P. Point P has coordinates A, B, C. Now I want to write, and I have a fixed distance. Fixed distance. Call it D. So P and D are fixed. P represents a point. D represents a number, a distance. These are variable. These are every single point in space that are D units away from point P. So P is fixed, right? This distance D is fixed. But XYZ is every point in space that's a distance D away from P. So how do we write that? So I want what? The distance from ABC to XYZ to be D. So can you write an equation that tells you that the distance from XYZ to ABC is a distance of D? Go, write that out. And make XYZ be the final point. So actually think about the distance from P to XYZ. The distance from P to XYZ. XYZ being the final point. So write out an equation that represents what I'm saying. That the distance from point P, ABC to XYZ is distance D. Write out an equation for that. Was there a William? There was a William, right? Where's William? Did you get it? Yeah. Just say it out loud, even though you haven't written it. Square root x minus a squared. All right. That it? Am I done? Okay, am I done? Equals D. And what's ABC again? Fixed. What's XYZ? How many points are there XYZ? Like this. Infinite number of them. Okay? So if I think about every single one of those points, what do I get?
Surfaces.
It's a surface, right? It's a surface. And it's, if it's equal distance away from a point, then it's going to be a perfectly round surface, right? It's going to be a perfectly round surface. Make this a little smaller. Actually, it's the best sphere I've drawn all day. Also the worst one I've drawn all day. So what are we representing? Every point, x, y, z. That's a variable point. But what's locked in about that point is always a distance d from p. That makes a sphere. Okay. Now so this equation then is the equation of that sphere. But usually we take the square root off when you write it equals d squared, and that's the radius, right? So x minus a squared plus y minus b squared plus z minus c squared equals, and I'm going to just change it to r squared. So d equals the radius of the sphere.
I'm not being considered the volume, correct?
What's that?
Consider the volume
Is that the volume?
or surface area.
This is surface area. It's every point. This represents every point. It's a set of points is what it is. It's not a volume or an area. It's a set of points that form the sphere. And it's all these blue points right here. Every single blue point that's a distance d away from p. So how much area that surface is or how much volume it contains is a different question. This is just representing the set of points that make the sphere. Is P one of those points? No, right? P is the center, but it's all the blue. Imagine all the blue points are represented by X, Y, and Z. Okay? So X, Y, and Z are a variable point. A, B, and C is a fixed or known point. Questions on that? Okay, I was hoping for more time on this, but we'll get started anyway. Any questions on a sphere? So, when you're given various problems about spheres, you can make sense of it by going back to what I emphasized here, right? That X, Y, and Z are variable, right? So when they get to the back, you're going to pass left and right when they get to the back, because I didn't count, okay? But by focusing on what I have explained to you, you'll be able to solve lots of different problems, although I haven't given you examples of those, okay? And then if you're in recitation today, you'll do one example of a sphere, okay? All right, so before we get started on this, next thing we're going to talk about is what's called, so we've seen scalar multiplication of vectors, right? Scalar multiplication is, for instance, 4 times you can take just a number, a scalar, and multiply it by a vector. And how do you do that? You just distribute it, right? It's going to be, and how will the new vector compare to the old one? What about its direction? Same, or if this is negative? Opposite direction. Either the same direction or opposite. So parallel. For sure, the vectors are parallel when you do scalar multiplication. And then what about the magnitude? 4 times greater, right? 4 times greater. So that's the vector 4 times of the original vector in the same direction. If it were -4, it'd be 4 times the magnitude, but in the opposite direction. Yeah, I'm sure it should be. talking and writing at the same time. Okay. Component form, 12, 8, -4. Okay, so now there's another kind of multiplication called dot product. This is actually you multiply 2 vectors together. We're gonna do everything in R2 first. So we're gonna do 2-dimensional vectors. So dot product is, if you say A comma B dot C comma D, here's the formula for it. A times C plus B times D. So notice what just happened. What is AC plus BD? What kind of thing is that? It's a scalar, right? It's not a vector. So when you do scalar multiplication, you multiply a scalar times a vector and you get a vector. When you do dot product, you multiply a vector times a vector and you get a scalar. Okay? And then here's what we're after. This is not about making cases, although that happens. What you'll see is there's cases that arise. When it's this situation, we have this. When it's this situation, we have this. Okay, that's okay. That's a good start. But really, we want to generalize this down to one principle. One principle of what does this final number mean? Those numbers that you're putting in the boxes. What does that, how can you summarize what that number gives relative to the 2 original vectors? So now, you're going to do the remaining 12 together. No. Okay. Let's hear some of your observations. So what were some observations that you came up with? Trying to make sense of this number that is the dot product relative to those original vectors. Jacob.
If the 2 vectors form a right angle, then it's 0.
Okay, so did you all find that?
Yeah.
All right, so we're going to kind of bank that in our memory. So this is going to contribute to our overall definition in the end. If they're at a right angle, we get 0. So what could that mean? All right, yes, sir.
It's not only that, but when it's at 0 degrees, it's a certain number. When it's at 180, it's a certain number times -1. So it leads me to posit that it's got something to do with cosine of the angle that
Okay.
the vectors are at.
Cosine, something to do with cosine, okay?
Could be a measure of how parallel they are together.
How parallel they are together, okay? What are other observations you made? So if they're perpendicular, it's 0. So, and then what about when they were in the same direction, perfectly parallel?
It's the greatest number you can get.
The greatest, and what was that maximum number? Did you?
25.
Okay, but
It was
in
squared.
general, generalize it.
Squared. 5 squared. The magnitude squared.
The magnitudes, the product of the magnitudes, right? The product of the magnitudes. Other observations. So these are all good. You guys are getting on the right track. So if you flip it over, you'll see. So when vectors A and B have the same direction, then what's the dot product?
Positive.
More specifically?
Max.
More specifically?
Magnitude times itself.
The product of the magnitudes of the vectors. In this case, 5 times, in your example is 5 times 5. The product of the magnitudes. So when they have the same direction, then the dot product is just simply the magnitude of A times the magnitude of B. Would you agree?
Yes.
Okay, so what else did you see? They're perpendicular. The dot product was 0. What's another one? Opposite directions is the opposite of the product of the magnitudes, right? Negative A times B. So I hope those next two, I think, are these two. Yeah, I hope. So let's just, so that's that one. This one down here. There we go. Oh, come on. There we go. So when there are so perpendicular vectors, we have a fancy word for that. When vectors are perpendicular, it's called orthogonal. And so the reason we have a special word for that is if we had an 8-dimensional vector, it would be very difficult to think of how that's perpendicular because we live in 3 dimensions and maybe the 4th dimension is time, right? But so when you have higher dimension, you need a term that's kind of analogous to perpendicular in what we understand this right angle. That's called orthogonal. Orthogonal is a general term for the dot product is 0. And then our example of that is perpendicular in R2 or R3. Opposite direction, then you get the product of the magnitudes. Okay, so then when they make an acute angle, so they're pointing in somewhat of the same direction, but not quite, then what do you get? You get a positive number, but it's less than the product of the magnitudes. That was like those second and third examples at the beginning. And then if you have an obtuse angle, so they're kind of pointing away from each other, so it's going to be negative, but not as big as the product of the magnitudes. So are you seeing a pattern to this? How about someone talked about cosine of the angle. Is this still fitting? When they're in the same direction, it's just the product. Now we get positive, but less than the product of the magnitudes, and then we get 0. And now they start to point away from each other. So now we get a negative value and the maximum negative value when they're all the way apart. Negative product of the magnitudes. So how can we sum that all up? The dot product is what? In one phrase. Yeah. Okay, so it has to do with the unit circle, but we're talking about what is that number? What is that number in the end? The dot product. It's a scalar. What scalar is it?
Scalar of how much? Like the magnitudes of the vectors come together.
Yep.
Times cosine.
Okay, right. So yes, we're seeing this very close relationship between the product of the magnitudes, first of all. You see that? But the relative direction then influences that. Yeah.
Are they like angles?
Well, the dot product is not the angle. It's the product of the magnitudes that's affected by the angle, right? Yes. It's the product of the magnitude affected by the angle. So it's the product of the magnitudes, what? In as much as the vectors are in the same direction, right? So if they're only partially in the same direction, you get the part of this one, or the component that's going in the same direction as the other one, times the magnitude of the other one. So that's where the cosine comes in, right? Because if you have A here and B here, then what is the dot product A times B? Well, it's the product of their magnitudes, but only in as much as they're in the same direction. So we want this much of A. If we took this much of A times the magnitude of B, we'd get the dot product. So what is this much of A? No.
Projection of A on
The projection, right? So it's the cosine, right? It's the magnitude of A times the cosine of this angle gives you how much of A is in the direction of B. And that's what we're going to multiply by the magnitude of B. So we're going to take magnitude of A times the cosine of the angle between the vectors times the magnitude of B. So how much are the vectors in the same direction if they're perpendicular? How much are they in the same direction? Not at all. Therefore, the product is 0. The dot product is the product of the magnitudes in as much as they're in the same direction. The degree to which they're in the same direction, that's the portion or the percent of the product of the magnitudes that you take. If they're not in the same direction at all, it's 0. If they're veering towards opposite direction, it's going to be negative, but less than what the maximum negative, which would be the opposite of the product of the magnitudes. This is going to be really important when we get to stuff in the end of the course, that you see that a dot product is. So this is the big takeaway here. The value of the dot product is the product of the vector's magnitudes as much as they are in the same direction. As much as they are in the same direction. So here's an alternate formula. So the formula I gave you at first, multiply the product, multiply the components and add them together. That's how you did the sheet. You can also calculate it this way. The magnitudes, product of the magnitudes times the cosine of the angle between them when they're tail to tail. Okay, we got to run. And so when you turn in your sheets,